1-5, absolute value functions. An absolute value function is just a function that contains an algebraic expression within absolute value symbols. You'll know if it has an absolute value because you're going to see these bars on each side of either a variable and or a number. The absolute value functions are often used to model situations where a value is constrained to be non-negative. For an absolute value function, f of x equaling the absolute value of x is the parent function. This means everything is based off of the absolute value of x, which is the simplest of the functions in a family. You'll notice in our diagram here, our graph, they are all going to be V-shaped. And because there's no the absolute value is always the distance from zero, it's always going to be positive. So in this lesson, when we look at these, you're always going to be above the x-axis. So some key concept, the parent function of absolute value functions. So a little bit more with the characteristics. So the parent function is just f of x equaling the absolute value of x. The domain is always going to be all real numbers because you can put any number in and it will still give you a value on the outside. The range will always be a non-negative real number because the distance from whatever domain you put in there will always be a positive value. The intercepts, the x-intercept, x will be 0, the y-intercept will be 0. So the vertex of an absolute value parent function would be at the origin of 0, 0. The vertex of an absolute value function is the highest and lowest point. So when we talk about the max or the minimum, it will be referring to the vertex here. So let's take a look at an example. It says graph the absolute value. So graph f of x equaling absolute value of 3/4 x plus 3 in the state domain and range. So for this one, if you want to draw a table of values, we can do that. This would be our x, this would be our y. We need to do our vertex. We'll eventually have to find a vertex. So let's just make it, just use numbers 0, -1, and 1. If I put 0 in for x, the absolute value of 3/4 times 0 is 0. The absolute value of 0 is 0 plus 3 will give us 3. If I put a -1 in there for x, I'm actually going to make this, let's make this a +4 and a -4. The reason why I'm choosing -4 and +4 is so I can get rid of the denominator, so all I have left is integers. So a -4 times 3/4 would give us a -3. The absolute value of -3 is 3. 3 plus 3 would give us 6. And then if I put a 4 in there, 3/4 times 4 would give us 3. Absolute value of 3 is 3. 3 plus 3 is 6. So now that I have a couple points here, now I can come to my graph and plot them down. So I have 0, 3. I have -4, 6. And then I have 4, 6. You can see my V shape. Now I can draw my line. And just make sure that there's no curve at the vertex because these are absolute value. So there would be my graph. Now I need to state the domain. The domain would just be all real. I can put any number in there and it will land on the blue line. The range is all referring to the vertex. So in septular notation, I could say y such that y is going to be greater than or equal to 3. Just means it's going to give me a number 3 or bigger. Next, graph f of x equaling the absolute value of x minus 1 plus 3, and then state the domain and range. Now I can draw a table of values again. Now to find the vertex, I can just use this part and this part to determine the vertex here. And the vertex here would actually be 1, 3. Because remember, the vertex is at 0, 0. So if I make inside here equal to 0, add 1 to both sides, and x would equal 1, that just means they moved the vertex one place to the right and then up 3. Now if I choose a point on each side, so 0, and let's choose 2. So if I put a 0 in for x, 0 minus 1 is negative 1. Absolute value of negative 1 is 1. 1 plus 3 is 4. 2 minus 1 is 1. Absolute value of 1 is 1. Plus 3 is 4. So if I plot this on our graph, we have our vertex at 1, 3. Have a point at 0, 4. And another point at 2, 4. So now I have enough for my graph. And then the domain, again, would be all real. The range, y such that y is going to be greater than or equal to, again, it would be greater than or equal to 3. Graph f of x equaling 3x plus 6 plus 1, and then state the domain and range. So again, let's just draw a table of values. Now another way to do the table of values is if we grab our calculator here, and in the y equals, we can graph this and then use the table of values to come up with our points and find our vertex. So here I'm going to hit the math button, go to numbers, absolute value is number 1. So if I click number 1 and then I just type in 3x plus 6 in parentheses, and then I'm going to have plus 1. If I do second graph, it's going to give me a table of values, and I want to see what my vertex is going to be. So you can see that it starts to repeat over here on each side of this 1. So my vertex is actually negative 2, 1. Negative 2, 1. And then I have my, I can choose points on each side. So I'm going to choose negative 4, 7, and negative 1, 4. Actually, let's do, this would be negative 3 and 4. Once I have those 3 there, if I want to hit graph, I could graph it, or graph it look like that. So our graph here, our coordinate plane, and then just plot those points. Our vertex is at negative 2, 1. So negative 2, 1 would be here. Then I have negative 3, 4. And I would have negative 1, 4. And then I can draw my V shape. And there's our graph. Domain, again, is all real. And our range, y such that y is greater than or equal to, this time the lowest part is 1, so greater than or equal to 1. Example 2, graph f of x equaling negative 2 times the absolute value of x plus 1, then state the domain and range. So here we have a negative coefficient. And anytime you have a negative coefficient, that is a clear sign that we're going to have a reflection happening here. So let's graph this. Again, we're going to come with our table of values. Now the vertex for this one, it didn't move up or down because there's no, so that the base format would be f of x equaling a times the absolute value of x minus h plus k. The k is up and down, the h is right and left. Right now, our h would be a -1. So this was moved one place to the left. So we can have our vertex is going to be at -1, 0. Now I just need to choose points on each side of a vertex. If I chose -2, -2 plus 1 is -1. The absolute value of -1 is 1. 1 times -2 is -2. And then if I put a 0 in for x, 0 plus 1 is 1. Absolute value of 1 is 1. 1 times -2 is -2. So if I plot these points, -1, 0, here's my vertex, -2, -2 here, and 0, -2 would be there. And draw our graph. You can see it opens downward, and the reason why it opens downward is because it's negative on the outside. Now we can state our domain. Our domain, again, our x's is all real. Our range, y such that y is going to be less than or equal to 0. Next graph f of x equaling -0.25 times the absolute value of 8x plus 3. Again, we're going to draw a table of values here. Again, if you want to put it in your calculator to come up with your table, you may do that. So for this one, there isn't any adding or subtracting from the x in the absolute value. So your x still remains 0. But this plus 3 tells you you're moving the vertex up 3. So my vertex is at 0, 3, and then I can just choose a point on each side. So I'm going to choose -1 and 1. So -1 times 8 is -8. The absolute value of -8 is 8. So 8 times a -0.25, or really it's 8 times a negative, or divided by -4, we would get a -2. And then if I put a 1 in there, 1 times 8 is 8, absolute value of 8 is 8. 8 divided by -4 gives us -2. And then I have to add 3 to the answer, and that gives us 1. Got to add 3 up to this one, so this would also be 1. Now I have enough points to put our, or enough coordinates to put our points down. So I have 0, 3. 0, 3 would be here. That's our vertex. We would have -1, 1, and 1, 1. Draw our graph now. It opens downward because of that negative. So again, our domain is all real. And our range, y such that y is less than or equal to 3. Example 3, here we're going to graph and interpret an absolute value function with a word problem. It says a digital thermometer being used with a patient reads 98.6 degrees Fahrenheit. The difference between the patient's actual temperature x and the reading on the thermometer is given by f of x equaling the absolute value of x minus 98.6. Graph the function and determine the key features of the graph. Then interpret the key features and the constraints in the context of the situation. So the first thing we're going to do is we're going to graph it. And we're only going to use quadrant 1 because I can only use positive temperatures. Somebody's not going to be in the negative, have a negative temperature. So based on what we have here, it's not going up or down. So the vertex is, it didn't move to the left or right, but it didn't move up or down. But it did move to the right. It moved to the right 98.6 degrees. I'm going to label my x axis, and this would be the patient's actual temperature. And we're going to count by 15s. So 15, and then this will be 30, 45, 60, 75, 90, 90, 105, 120, 135, and then this would be 150. So now, if it moved 98.6 degrees to the right, I'm going to put about, since this met between 90 and 120 would be 105, between 90 and 105, halfway be almost 98. We'll put a point roughly here. So that's our vertex. Let's put that down. Vertex when x is 98.6, our y is 0. That means we could do the intercepts here. The x-intercept would be 98.6 and 0. And we'll get to the y-intercept shortly. So from that point, if that's our vertex, we can choose points on each side of that. So if I were to put, let's just choose, the y-intercept. So for the y-intercept, f of x has to equal 0. So what does x have to be to make this equal to 0? The x would have to be 98.6 for y to be 0. So if I count the y-axis also by 15s, so that means 15, this would be 30, 45, 60, 75, 90, 105, 120, 135, 150. We would have a point roughly here. And we have enough to draw a line here. And then this one, we're going to bounce off this direction. That means our y-intercept is going to be 0 and then 98.6. When is this increasing and when is it decreasing? So we can say it's increasing. I'll use I for increasing. It's increasing when x is 98.6 to positive infinity. So that would be designated by this bar over here. It's increasing here. And then it's decreasing. I'll use a D for decreasing. And it's decreasing when we have negative infinity to 98.6. It's positive. It's always positive. And we can show that by negative infinity to positive infinity. The end behavior you're going to have as x increases, decreases, your y is going to approach positive infinity. It's always going to increase. And then symmetry is symmetric. Around the line when x equaling 98.6. Because if I were to draw a dashed line through here, it'd be mirror images on both sides. So now then we forgot the domain and range. The domain here, domain would be all real numbers. And the range would be y such that y is greater than or equal to 0. But if we were to be more accurate with this, it couldn't, like the domain couldn't be all real numbers because you're not going to have negative temperatures. So technically, it's only a difference of a couple of degrees. So a good domain would really be 90 to like 105. Anything below 90 and above 105, you're in danger, or you'll probably be close to dying with it. Your body's going to shut down. That would be a good range for or the good domain for this particular problem. Next, Roman rides his bike at a constant rate from his house and then back again. The distance in miles g of x from his house after x minutes is represented by the function g of x equaling negative 1/6 times the absolute value of x minus 30 plus 5. Graph the function and determine its key features, then interpret the key features of the graph in terms of the constraints of the context in this situation. So the first thing we need to do is determine how we're going to label our axes. So the time is going to be our x. And our time, let's count those by tens. So this would be 10 and 20, 30, 40, 50, 60, 70, 80, 90. And then our y value, our y axis would be our distance. And we will count those by ones. This would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now we're just going to use information that they gave us here. We can see that our vertex is going to be at 30. So it went 30 to the right, and it went up 5. So this part and this part tells us the vertex. So if I go 30 up to 5, that's our vertex. And since this is negative on the outside, I know it's going to open downwards, so that's our maximum. Now, if I put if x was 0, I put 0 in for x. 0 minus 30 is negative 30. The absolute value of negative 30 is 30. 30 times a negative 1 divided by 6, or 1/6 gives us negative 5, and plus 5 gives us 0. So I would have a point at 0, 0. It just means if his home is at 0 miles away, he didn't go anywhere, so the distance he traveled is 0. So 0 time, 0 distance. So if that went 30 to the left of the vertex, if I go 30 to the right of the vertex, that would be here at 60, 0. I would now have my absolute value graph or function. Now we're going to use that and interpret the key features. First off, the domain. Here the domain would be in this particular problem, our domain would be, we could say negative infinity to positive infinity, but with the constraints, the better way of saying this would be x such that x would be greater than or equal to 0, but less than or equal to 60. Because they were only gone for an hour. Now the range, here we would have y such that y is less than or equal to 5. because he never went more than 5 miles away from his house. Vertex is at 35. The intercepts, the x-intercept would be 0.60. And that is just saying that, actually, the x-intercept would be, it would be 60, 0, and 0, 0. So once he hits 0 minutes, he's at his house, and he went 0 distance. But if he goes 60 miles, or 60 minutes, then he would be at 0 distance, which means he's back at home. And then the y-intercept would be 0, 0. Just means he went 0 miles at 0 minutes. Increasing and decreasing, it's increasing, and we'll get our range for that one. It's increasing from -infinity to the 30, and then it's decreasing from 30 on the low end to 60, or to positive infinity on the right-hand side. If we want to be more specific, then we could say it's decreasing from 30 back down, but that's fine what we have right here. Then it's positive. This one's always positive. Well, for this one, we would say it's positive when it's between 0 and 60, and it's negative. If we were to continue that, we would say that it's negative from -infinity to 0, and from 60 to positive infinity. If I go back to the graph, they're just saying that it's negative over here, and it's negative over here, and it's positive in between. Next, the end behavior. The end behavior, they're both going down, so as x increases or decreases, our y approaches positive infinity or negative infinity. And it's symmetric when x equals 30. And the constraints, we just said the constraints in our domain and our range. And if we were to do our range a little bit better, the constraints, we would really say it's between 0 and 5. I use brackets because it can equal 0, and it can have 5. It can't be anything less than, so when it says y is less than or equal to 5, that would include negative numbers, but the constraints, you can have negative distance. And our last question, Liam is playing a game of pool. He hits the cue ball so that it hits the 8 ball located at 515. The 8 ball travels along a path that is given by f of x equaling the absolute value of x minus 20. The 8 ball enters the corner pocket at 4020. Graph the function and identify the key features in the context of the situation. First thing we're going to do is count or label our axes. Our x-axis we will have as our, or count by fives. I'll do 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, and do the same on the y's, 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50. Let's label our vertex. So it says that he hits the cue ball so that it hits the 8 ball located at 515. If I put a point at 5 and 15, travels along a path that is given by f of x equaling x minus 20. The 8 ball enters the corner pocket at 40-20. So if I put a point at 40-20, that would be right here. We need to graph that function. So if we were to graph that function, we're going to have to find the vertex on that one. And the vertex can be found by using this number and the number on the outside. Since there's no number on the outside, that means it did not go up or down. So our y is going to be 0. And this means 20 to the right. So 20 to the right, 0. So I had to have a point here. And then I can use my graph or numbers or a line graph the points. And then we can put a dash, just meaning that it went through the hole there. And there would be our graph there. Now we're going to use that to identify the key features. So the first part is the domain. The domain is going to be between 5 and 40. If we go back to here, it says it hits the cue ball, so then it hits the 8 ball located at 5:15, and the 8 ball travels along a path that is given by f of x equaling x minus 20. So the ball is being hit from over here. It's going in this direction. It's where the green dot is. That's the 8 ball. It bounces off the wall and then goes into the pocket, which is at 40-20. Now our range, so this is our domain. Our range is going to be, and here we're going to have from 0 to 20. It doesn't go more than 20. You go back to here, it doesn't go more than 20. It doesn't go less than 0. So our range would be 0 to 20. The vertex, we had our vertex at back to here, vertex is at 20, 0. The x-intercept is the vertex. This would be 20. And the y-intercept, there is no y-intercept. So if we go back to that, you do not see where it crosses the y-axis because the ball is one of the passes the top solid point. So if I put a point back here, and this is just dashed. So the solid line, yellow line, that's where we're looking at the path of the ball. So that's between, it never crosses the y-axis on that. Next, increasing and decreasing. It's increasing when we're between 20 and 40. And it's decreasing when we have between 5 and 20. Positive and negative. This one's always positive. End behavior as x increases, decreases, our y approaches positive infinity. And then is there symmetry? There is symmetry when x equals 20. That is our lesson on absolute value functions.